Welcome to the exercise of the lecture Pattern Recognition and Machine Learning. Today is number 8 of the exercise, and today's topic is speaker and speech recognition. Today we will talk about first a small review of speaker and speech recognition. I will start with speaker recognition, and afterwards I will tell you something about speaker recognition. After that I will go through some comprehension questions, and at last I will show you some Python code. Let's start with the first half, the speaker recognition. For that we can classify speaker recognition in different parts, and this is the overview of each part of that. We start at the top, of course, and go through each of those boxes, and I will talk I will tell you something about each of those boxes. At first, when or for what we can use speaker recognition. Of course, that's, for example, if you want to personalize something, or you want to restrict some access to somebody. So you would use voice recognition. So you can say, hey, that is speaker 1 and that is speaker 2. And speaker 1 has certain administrative control that speaker 2 doesn't have, for example. There's a big split in that. The first one is speaker verification. That has the assumption that we have a certain set of possible speakers, and we want to look if the speaker under test is in that group and has some sort of access to the restricted area. So somebody talks, and we control, or we look up if that speaker is in our database or not. That can be split in two parts. The first version of speaker verification is text-dependent speaker verification, where we just have a predefined text that the person has to read, and we control if that text or that features are in our database or not. The second is the more free version. This is a text-independent speaker verification, where we have features that don't depend on the text that the person has to speak. Yeah, speaker verification is a little bit more simple than speaker identification, because we only have to check if that person, or we have to rule a decision if that speaker is in the database or not. The second method is speaker identification. So we not only want to look up if that speaker under test is in our database, but also if it is in our database, who of those speakers that are in our database is the closest one to our new speaker. So we have there are two sets, the closed set speaker identification. So we have pretty much just a predefined number of people that are in our database, and this database gets recorded one time, and then we have our speaker that we will compare to. There also is the identification if we want to use text-dependent or text-independent speaker identification, but those are pretty much just the same cases as in the speaker verification. The second subgroup of speaker identification is the open set speaker identification, where we have not only a database with speakers, but can also extend this database. If, for example, the speaker is recorded and we don't have it in our database, there's a possibility to extend our database with those just recorded voice recordings, and we can extend our database. For that is also the split in text-independent and text-dependent speaker identification, but those are again just the two versions as before in speaker verification. Here is the overview of speaker verification. So we have input, a speech signal that gets recorded, and we want to look if that speaker is in our database or not. So it's a binary decision that is the result. So for that we have our input y of n, and afterwards we do some steps that I will go through with you. The first part is distortion, reducing pre-processing and segmentation. In that part we want to make our input signal y of n as best as possible, so we can produce or we can calculate of the best version of that signal. So we want to reduce, for example, the noise, any sort of reverb. We want to also use only the speech signals, so we use segmentation, and yeah, we want to get our chances as best as possible for recognition the speaker of that speech signal. This is often done by going in the frequency domain, and this is done with a short-term Fourier transformation. So afterwards we have our estimated short-term spectrum of the signal that is hopefully better than the input signal before. The second part is the feature extraction. What we're doing there is, again, we use some, or we apply some feature extraction. So our model that we build are built on features, and we have to extract them. So we pretty much just calculate them in that box. Important part is the normalization, because, for example, if a speaker has a very low microphone in one part, and the other speaker has a microphone that has a higher gain, we want to neglect those input distortions, or not distortions, but input factors, because we only want to focus on the speech and not on the gain, for example. So we have to normalize our input features. After that we have our features x of n, and those features are going in our model for our speakers. In this case we only control it with one verified speaker model. So we calculate the distance between our feature input vector and our model and get an output out of it. Besides the model for the speaker to be verified, we also have a uniform background model. This model is filled with speech, or trained with speech signals from other speakers, multiple other speakers, because it's just a model that we use for comparison to our verified speaker model. So we put our feature vector in both of those models, and afterwards we compare the probabilities that the feature vector x was produced by model, the verified speaker model or the universal background model, and we compare those probabilities with each other. And if one probability is higher, it's more likely that this feature vector was generated by those model. So if the probability for the verified speaker is higher, it's probably the verified speaker speaking. Otherwise it would be probably just another speaker that is not the verified speaker. So afterwards we just have a binary decision, and this is either 1 or 0. So it is the verified speaker or it's not. And what we can do for training, we just use a binary decision model and feed it back in our model, so we can train our verified speaker model if we know that the person just spoke is our verified speaker. The second part was speaker identification. And for speaker identification, we have the same beginning. So we also have our y of n, our input signal, that gets to the distortion, reducing pre-processing and segmentation, where we, for example, reduce noise and only let voice signals through. So we have a voice activity detection, for example. And afterwards we get our short-term spectrum that will go into our feature extractor, where we also do the normalization, for example. Afterwards we have again the feature vector x of n, and now we want to identify our speaker. So we have many, or not many, but more than one speaker models, and we compare, or we calculate again the probabilities as in speaker verification. Those are those outputs here. Again, we have a universal background model that is filled with the speech of other speakers for comparison. And what we can do is we can calculate again the probabilities and look up which is the most probable speaker of those models. If the universal speaker model, for example, is the winner, we may also generate a new speaker model or create a new speaker model with training. So we would look at the output and look if the universal background model is depicted, and would just train our model with those input signals. Now we can look at the different boxes before. So at first I will start with the distortion, reducing, preprocessing and segmentation, so that you get a better idea of what we are doing there. And afterwards I will go through one small feature that we are using later in the Python code. So let's start with the distortion, reducing, preprocessing and segmentation. As before, I said that's, for example, noise reduction. And this picture should be familiar to you, because this is just a picture of a Wiener filter. And this should be handled in the first exercise, I think, where you already programmed a Wiener filter. But a short summary of it: we have an input signal, y of n, in the time domain, to an analysis filter bank where we get our short time spectrum out of it. And we have an noise estimation where we estimate the noise part in our signal, and an input PST estimation where we estimate our received signal spectrum. And those two spectrum are getting filtered with the Wiener filter part of it. So we have some filtering in it where we reduce the noise, and afterwards we multiply our original spectrum with those filter coefficients and get our noise, hopefully noise reduced signal out of it. The only part that is different to the part in the first exercise is the segmentation part. The segmentation part is this arrow here, and this arrow closes the gap between that if we have a certain criteria fulfilled. For example, this would be in voice activity detection. If we have for example, only noise detected in this frame, this loop would not close, because of course we don't have voice in it, and we would not have an output, for example, or only zeros in the output. And for speaker recognition, it's not suitable that we look at noise, because noise don't depend on the speaker itself, so we wouldn't find any useful features in our signal, so we don't need to process this frame at all. And if we look at the output of those things, for example, we can look at the spectrum or the spectrogram. When you look at the top, we have our normal input vector y of n. That is a little bit noisy, but we can see that we have noise here and so on. And the first part is the Wiener filtering of it. So we reduce the noise, that you can look at the amplitudes of the signal. In the low bands it's less noise, for example, and in the mid, but we can also see that the speech signal is more clearly visible in those areas. And afterwards we do the signal segmentation, in our case voice activity detection, where we just use the frames where we detect some sort of noise. This could be, for example, a very basic noise estimation where we look at the power, the short time power of that frame. If it's high, we assume to be speech. If it's low, it's maybe or it's probably noise. But there are more advanced versions of voice activity detection with neural networks, for example, that will do the job maybe even better. And yeah, that's summed it up for distortion, reducing, preprocessing and segmentation. The next part would be feature extraction. And for feature extraction, you already had an exercise as well. where you learn something about LPCs and some other features that you can extract from signals. What we want to look here is the Mailband coefficients, or MFCCs. The MFCCs are getting calculated from the short-term power spectrum, and at first we calculate the squared, or only the magnitude of it. Afterwards we apply some Mel filtering. Mel filtering is just a mapping of the values to a certain other mapping. So what we want to do is we want to process speech, and for speech there seems to be a very distinct feature that the Mel filtering is very good at differentiate between speech parts of it. So we apply this Mel filtering, and afterwards we calculate the logarithm of it, which makes the signal more viable, and afterwards we calculate the discrete cosine transform of it. And at the end we have the MFCCs, and those shown that they are very good at as feature vectors for speech parts, or for speech features of it. So if you want to do something with speaker verification or recognition, or even speech analysis, those MFCCs are very good for some sort of this sort of application. Okay, that pretty much sums it up for speaker identification. We talked about the pre-processing and the feature extraction. The last thing we might talk about is the adaptation that we can do. Let's assume we have trained a model for speaker 1. It's called speaker model 1, and this model was trained for a time X, maybe for 30 seconds or something like that. And that was it with training the model. But if we maybe have a lot of verifications or identifications in the time, we can adapt our model, because we have more and more new data. Every time somebody or that speaker gets identified, we have a new set of feature vectors that are pretty much verified that speaker, so we can use it for training. This process is called adaptation, and if you look at this picture, we can pretty much see what the problem is. We have trained a model on the left side, and it fits okay-ish, but in the time we use that model, we get new feature vectors, and we want to adapt those. So there is a possibility that we can adapt our Gaussian distributions with the time of verification and identification. The second part of this lecture is speech recognition. This part is a little bit shorter because it has a lot to do with speaker, or it has a lot to do with the principles of speaker identification. For that we need to get an overview of what speech is, in the sense of what parts of it contributes to that message, to the creation and the understanding of the message. So the first part is that we create the message. So this might be as a thought in our head. Afterwards we create the words in our head, so we know what we want to say. And then we go to the physical part of it, where we actually move our muscles. I think this was already discussed in the exercise of bandwidth extension, where we looked at the processing of speech in our mouth. So we have the vocal cords that will generate an excitational signal, and the vocal tract that is a filter for that. And after that we have our acoustic channel that transmit the sound waves from one person's mouth to another person's ear, and that will move our membrane in our ear. And after that, we have pretty much the same process as before, just the other way around. So we have neuronal activity, and we transvert or convert those sound or those signals into language, and afterwards we have to understand the message of the words. So this is pretty much a speech transmission. Okay, let's have a look at the technical side of view. So we have this part, or this signal flow of speech recognition when you want to apply it. The top part is during runtime. So this is a part that runs on your cell phone or your computer, something like that. And the bottom part is the training. This is often done beforehand and used by the runtime version of it. Sometimes the training is also done in real time. So if it learns something new or something like that, we also adapt our models, but the basic part is done by a company, for example, and shipped with your device. So at first we look at the top part, the runtime part. So we have our speech signal. This might be sound waves that are recorded over a microphone, or maybe speech signals as a WAV file. Later in the Python demo, we will use FLAC files, and those are just speech signals. Those are going in the feature extraction, where we extract our features. This could be, for example, Mfcc coefficients, or also APCs. And afterwards, we go in the decoding phase. In the decoding part, we use two models, the acoustic model and the language model. And afterwards, we get our vocabulary out of it. So the most important question is why we use two models. We can look at it at the acoustic part of it. This is pretty much very similar to the speaker identification and verification. So we have a model that is trained for maybe some sort of words or some sort of phonemes, and this will give a certain probability that our feature vector x of n has this probability to a given model. So we can say, hey, those the most probably word that there was spoken was word X. And the second part is a language model. This is a little bit more advanced, because we also look what we already have recognized and put it together in a speech language model. So some words are more likely to go after each other, or some phonemes are more likely to go to follow each other than others. And this has also a given probability that is pretty much just dependent on the state. And those two probabilities get multiplied with each other, and will give you a certain probability that the word that was spoken was word X. And this is pretty much speech recognition. So you can see that there are a lot of very complex parts of it. The model, the combining of the model, which model you will use, or which features. And that's pretty complicated. The training part is pretty much this a very similar way. But we need for training is we need labeled data. So for this, we need to know what there was said. So we need some sort of training material, for example, speech signals, if we want to train speech recognizer. That goes also in the same part, in the feature extraction and everything like that. And for each of those speech signal data, we also have in text. And that text will also get in a text processing part of it, where, for example, we analyze which phonemes are in it, or what was said in which order, for example. And those two outputs of it will go in a training model, or a training part of that corresponding model. Of course, the speech signal will train the acoustic model, and the language or the text data will train the language model. And that's pretty much it for training. Afterwards, we just combine it and look at the output. This is the more detailed way or signal processing way of our speech recognition. So this is pretty, or has some pretty similar parts to speaker verification, identification. So the first, so we have our signal as input vector. We do some pre-processing. This might be, again, noise reduction with Wiener filtering, segmentation for only using the voice parts, something like that. Maybe even beamforming if you have multiple microphones. After that, we have a more optimal or better signal, and that goes in the speech in the feature extraction. There we want to extract the important part of that speech signal. This might be LPC or MFC coefficients, and from that we also we want to use less data, so we only want to use to extract the important part of it. Afterwards, we do some classification. In the classification, we want to look up the best fit for our input. So we calculate for each model that we have trained the probability and give those the most probably ways out of it. And our speaker verification, identification, for example, are those the models for each speaker. In speech recognition, this might be models for some certain words or phonemes, for example. Afterwards, we have some sorted and not sorted, but some output that has the highest probability, and we need to find a decision. And the decision is based on prior information. For example, some words will appear after another, or are very likely to appear after each other, or some phonemes have very high probability that they translate from one state to another. This decision part is often done with, for example, an HMM, a hidden Markov model, that was talked or was the topic of the exercise before. And in this part, we also have the time domain of it. So we have we know what we choose before, or what the states were before. So we can put more information in it and get a better decision out of it. And the last part is just the output, and this is hopefully the correct text. At last, here's an example for such a hidden Markov model that maybe is used. This is an example in the German language. So we have the numbers 1 to 9, and in the German language we always connect a two-digit number with an und, which is an and in English. And afterwards we have the big numbers, so the first letter of a two-digit number, for example, which might be 30 bis 90. And this pretty much shows the concept of a hidden Markov model. So we have at first always number 1. Afterwards we always have an und. And the last part is always its second number. So we always go through the state und and go then to the next state. So if we connect those in a hidden Markov model, we will always translate to the second und. So we can choose the number dependent on this hidden Markov model, for example. This will help a lot. Okay, this pretty much sums it up for the review of speaker and speech recognition. Let's come to the second part, the comprehension questions. For that, I prepared, I think, 3 questions that we talk a little bit about. The first question is, what is the meaning of discriminative training? Discriminative training is when you train a model for only once, or you only train independently of the speaker. So you have data for speaker number 1, for example, and train your model 1, and you want to optimize, of course, that model to that given input. And that is done for each speaker independently. So you also train your model, your second model for your second speaker, in the way that you maximize the fit of the model. The problem here is if you have two speakers that are very similar and will produce very similar models from that. So you might have problems if you have a little bit variation in the input. For example, you have noise, you have a different microphone gain or something like that. This will maybe lead to small changes that changes the input, that it might be wrongly detected. So you have speaker 2, but you have the highest probability for the model number 1. And this might be a problem. So to neglect this problem, you use discriminative training, where you train all of your models, for example, GMMs, with the regard to each other. So you want to not to maximize your model fit to a given input feature set. You also want to maximize the distance to all other GMMs, for example. So you have a more constrained way of training your model to optimize it, but also to maximize the distance to another GMM. And this will lead to better performance in the sense that very similar models don't mix up. The second question is compare the evaluation results of speaker recognition based on codebooks and GMMs. Yeah, and those results or this comparison is pretty easy, because we have these numbers, and we see that pretty much for every number of codebooks on Gaussian distributions, the codebook approach is worse. So we see that the Gaussian mixture model is pretty much always better. This is due to the more complex version or more complex model of the Gaussian mixture models. So we have a more complex way of distinguish between different feature inputs. The problem with the GMM is, for example, that it's just more complex, and we need to calculate more, or we need to train more in a more complex way. But if we have the time and the horsepower to do all those calculations, it's pretty much better in every way in this case. The last question is, what is a semi-continuous HMM? How can memory computational load be reduced using semi-continuous HMMs? For that, we can first look at the explanation of semi-continuous HMMs. So semi-continuous HMM is a model where we, for example, use only one Gaussian distribution instead of many Gaussian distributions per state. In this picture, for example, we have 2 states or 4 states with the final and the initial state, but 2 normal states. And in this, we could, for example, only calculate our mean and our covariance matrix once, or the vectors once, and use those as an input for all of our states. So in this case, we would calculate it once and go and put it in our states as, for example, just the vectors in it. So we can save memory and computational load in the sense that we only calculate Gaussian distribution at the start of this training, and also we don't need to compare every of those in each of those states. So we can save memory in that. And yeah, we can also reduce the number of Gaussians for each HMM, or restrict that number of Gaussians for each HMM. And yeah, we can calculate the base Gaussian only once. Yeah, this pretty much sums it up for the comprehension questions. And now we can come to the last part, the Python demo. Okay, let's go on with the last part of this exercise, Python demo. For that, we provided you some data, some files with it. So we have in the folder two speaker files, speaker identification files, one DIY and one solution file, and 2 GMM support files, again one DIY and one solution file, and requirements.txt if you want to install a virtual environment with it. There's also a database folder in it, and this database folder has some files in it. And what we want to do with this exercise is that we want to train a speaker identification software with GMMs. And for that, we want to train our model for 4 speakers. Each for them has his own folder and a universal background model, the UBM. And after we trained those 5 models, we want to test some data, some files that we don't know from which speaker they are. And we want to identify them if we already know the speaker or if it's an unknown speaker. If you want, you can click around a little bit in those folders and listen to some of those files. It's just normal speech in English.
While they were talking, the baker had taken the apples which the girls were to eat for dessert and had sprinkled a sleeping powder over them.
This was, for example, speaker 3. Speaker 2 is this one.
Add 2 tablespoons thick sour cream, 2 tablespoons sugar, a sprinkle of mustard, and half...
some guy. And those are the 4 models. In the universal background model, we have many speakers, so you can see that the speakers have different front numbers. So all numbers from 48 are the same speakers, all numbers from 2078 are the same speakers, and so on. So in the UBM we have a lot of speakers because it's a universal background model where we need a lot of different speakers. And all of the speakers itself have the same number in the beginning, so these are all files from the speakers. So let's start. I will start with the DIY version of it, so the speaker identification DIY. At first, we have some imports that are also in the requirement.txt, so if you install the virtual environment, you don't have to worry about it. We just use NumPy for all the math stuff, sound file for loading the files, matplotlib for plotting the stuff. We have a more special version, a Python speech feature package that we need to calculate the Mfccs, and we also have a package for voice activity detection, WebRTC-VAD. I think this is a voice activity detection from that uses that Google uses, or some parts of it. It's probably the light word version of it. And we also import some functions of our GMM support file. This is a file that you already should know from the GMM exercise. I added one function that you later need to fill in by yourself in the DIY function, but the rest is just copied from the exercise before. Afterwards, we have 3 functions that I will go through in a minute when we reach them, and the main file starts here. So those are the parameters you can later play around a little bit with. For example, we can change the length of the training data set in seconds, so the length that we train our GMMs with. We can also change the length of our testing data that we later use for testing purposes. At the moment they are both set to 1 second. In theory you could change it to every value you want, but you need to keep in mind that you don't have infinite speech signal, of course. So I set the limits, or I recommended limits from 0.5 seconds to 100 seconds. The third parameter is the number of Mfccs. This is also a nice parameter that you can play around with, where we choose the number of Mfcc coefficients of the feature vector size. that's basically it. The seed variable is a seed for random number generators. So if we set the seed, you will also get the same numbers or the same random numbers as me, because we use the same seed. If you don't want to use the seed, you can say none as a type, and every time you will run it, you will get different results, slightly different, but different results. The next parameter is the number of Gaussians for the GMMs. This is just the number of Gaussians you use in your GMM model. I set this to 1 at the moment because it's the fastest version, of course. You don't have to train as much as, for example, 5 or 10. If you set this number higher than 5, it will take some time to train, but in theory you could also do it to infinity. The next parameter is the maximum iterations of GMM. I set this to 10 because after 10 iterations we don't need to go any further. Often this is enough. And the last parameter is just if you want to plot your feature vectors. I set this to true so we can later see what features or how our Mfcc coefficients look like in a plot. After that, there are some initialization variables that don't change with this setup, or you can't really play around with because they are given. For example, number of speakers. In theory, you could also add a speaker if you want to use your own voice or something like that. You can record some of your sound files when you're talking and store it in the folder number 5, for example. And can train the model with your voice if you want to. You only have to remember that the sample rate should be the same, but this is easily done with Audacity or something like that if you have a different sample rate. Also we can, here's the voice activity detection frame length set. So we use 20 millisecond frames for our VAD, and the other are just the folder names that we defined. And now we can start with the training of the models. So we have at first, if we set a seed, we initialize our random number generator with the seed, and afterwards the training really starts. So we go through each of our folders, load the data, so we can have a small look in the function. It's pretty simple. We just open the file in the folder, read the file and the data, and append it. So if we have multiple files, we all append those sound files to one big vector and return this big vector. So that's pretty much it. The next function is the extract voice only data. So for that we give the all data in our function, also sample rate and the VID length. And what we are doing there is we split our data in those frame length of, in our case, 20 milliseconds. So we only have afterwards our long vector divided in the number of frames that are all 20 milliseconds. And afterwards we look with our package as VAD if the containing frame has speech components in it or not. The resulting vector is just, or the resulting number of this function is just a bool. So we store it for each frame, and afterwards we insert it in our data and only have our frames with speech in it. Because we before splitted those in frames of 20 milliseconds, we want to flatten our signal, that we have our long big signal again. And this only speech signal only contains speech components and no noise, for example, and those. Afterwards we have now our voice signals, And we are done with the pre-processing. Afterwards, we now come to the calculation of the MFCCs. For that, we have also the package PSF and the Mfcc package. And if you want, you can read the documentation of it. But basically, we just compute the Mfcc vectors by frames. So we define here our window length and our window steps. You don't need to look at it, but our window length is the same as the VID length, and the window step is 50%. So we have overlapping of 50% in our Mfcc coefficients. What we also said is the number of coefficients, and this number varies from the parameter set. And afterwards we have our MFCCs, our feature vectors. So this vector contains our data in frames, and each of these frames has the number of MFCCs as a second dimension of feature vectors. And the last part is that we now have a lot of frames, but we want to split it in our training data. This is the last function we have, where we just has an input of our signals, which is frames times number of MFCCs. And what we want to do is we want to pick random frames out of it. And those random frames would have to be a certain length, the length of the training data set in seconds. So at the moment we have all of our WAF data sets appended in the signal. This might be a few minutes of data, but for training we only want to use a certain amount of seconds that we defined beforehand. So we pick random frames out of it. This is this part, and append it as long as we have our set length in seconds. We have to be a little bit careful because we picking the frames random. We don't want to use the same frame twice. I mean, this is pretty unlikely because we have in this example, this explicit example, a pretty big number of frames and a relatively small number of training data. So we pick very few frames, but for safety reasons, we have this if statement that we don't use the same frame twice. And afterwards, we have our training data prepared. It's splitted. It's only voice. It's converted in MFCCs. And with this data, we can now train our model. So we do this beforehand for every folder. So for each speaker, each of our 4 speakers, and the universal background model. And afterwards, we can train our GMM with the EM algorithm for each of those 5 different models. So we go through of each of those models, of each of these datas, and calculate the EM algorithm with it. And afterwards we need to test the data. So we go, we load our sample data in, and this is in the folder unknown. So the database we have our speakers and the UBM and also the unknown folder. And we pretty much do the same. So we extract only the voice of it. Afterwards we calculate the MFCCs. And there you have to insert some of the code yourself. This is not very complicated, I think, but you can have a look if you want to. Afterwards, we have our MFCCs that we need to split in our training data. And afterwards, we have to classify our data. And this classification is a function in the GMM support function, a file. So if we look at it, we have at the very bottom this function, so you also have to insert some of this by yourself. You can think about the classify probability pretty much very simple, because instead of one sample, we give many samples as an input. So we need to calculate the logarithm of the probability for each sample. And afterwards we need to return the highest probability of those values for each of those classes, and it needs to be one number. So you can think about for yourself what you need to write in here. Afterwards we have classified our data for each of our unknown file and have depicted the model with the highest probability. And the last part is just writing the file names and the estimated speed in the console. And if you want to, we can plot the feature vector as an example. And yeah, this is pretty much it. Now you can work on your own, and I will give the solution in a minute. Yeah, now you have done it by yourself. You can look at the solution. So for that, we need to look at what was the first question mark you have to fill into. 137. So if you look at the line 137, you had to insert the Mfcc functions. That's pretty straightforward because you could have copied it from the call beforehand. So in the top, we also use the Mfcc coefficients to label or to calculate our feature vector, and we really have to copy it just because we already have the same the same name for the input variable. So we need to insert only speech, the sample rate, and of course a number of Mfcc coefficients. So this number has to be the same as before, otherwise our model wouldn't fit. The next question mark was in our classify probability function. So for that we need to look at our function and what it wants as an input. So we have the samples and the models. We can already see that's pretty much the classify function, but we have the plural of samples. So we need to insert here our whole samples, which is ppf splitted features of unknown data. This has the dimensions samples times feature vector size. And afterwards we also have to insert our model list so we can compare to. And yeah, this is pretty much the input of this variable. If you look at the GMM support file, there were two question marks, and I will explain it, what we need to insert. So we have now our samples, so our x of n as an input, many samples with the size of the feature size. For example, 500 samples times 13 or 5 vectors with the features. And our models are 4 speakers and 1 UBM, so our models are 5 models that we go into. Afterwards we need to define the number of classes. This is pretty easy, and we need to calculate the probability that those samples are the probability of the models to the samples, that those samples are from that model. For that we calculate the log prop function of all of those samples to each of those models. So we go through each of the models and give it as a parameter and the log prop function, which is here. And the log prop function returns calculates the probability that all of those samples are from that specific model. And we need to do this pretty much just for all of our classes and store it in our probability vector. Afterwards we have for each of our models a probability that those samples are from that model, and we just need to calculate the maximum probability of it. So we return just the model number, so the index of the highest probability from that for that sample size. And if you look at our solution, we have then our number or our model ID and dependent in our classified list, and afterwards we just print it out. So we can run the model, and it depends on your parameter size. It may take some while. In this part we picked pretty pretty low parameters, very low training set, very low data set, and not many MFCCs or Gaussian GMMs, and we have our result written here. So we can look at the files, and it will tell you which estimated speaker it thinks or the model says it is. So we know that our speaker number 1 has the 251 as the first 3 letters. So if we look at our unknown vector, we have also the 251 here at the first variable, as the first file, and we look at in our path, we have it as the third, and we see that our 251 file has classified as an 1. That is correct. So that worked. And we can do this for all of our models. So the second speaker has the 652. It's this file. And the 652 is in this line, but there's the first mistake. It also is classified as speaker number 1, and that's clearly wrong because they are not the same. And if you look through all of those files and all of those numbers, we see there are more mistakes. For example, the 76 is our third speaker, 79, 76, and it's classified as our universal background model, or as an unknown speaker. And this is also wrong. What we can do is we can increase some of our variables. The most efficient way, as I found out, is to increase our MFCC numbers. For example, we could use 13 MFCC coefficients or MFC coefficients and run the model again. This will take a little bit longer because we have more things to calculate. Okay, pretty fast. And now we can look at those output values again, and we see 251 is again model 1, that's correct. 652 is our second speaker, this time it's correct. We said 7976 was our third speaker, this is also correct. And our fourth speaker has 7850. Is this file? This is also correct. So the other files that were in here were just random speakers, so we also had to give them pretty much the UBM, because we don't classify those as 4 speakers, just in the background model. And as we can see here, those were also classified correct, because the first one and the second and 3170 and 6241 are all our not trained speakers, and they should have be classified as in our UBM, and they are classified in our UBM. So this worked pretty good. What you can try out by yourself, a different combination of it. The last thing I want to show you is the plotting of the Mfcc features. So for that we have here this part where we just plot for the first frame every of our Mfccs. For the first model, so for the first speaker, the 0th speaker, which is in our database the first speaker. That's a bit confusing, but you have to remember that we are Python. So we start at 0. So we have our first speaker in 0 and just our frames and our Mfcc coefficients. And if we plot it as an image, we can see that we have here our image. So we have our 13 Mfccs and our, I don't know, like 100 or so frames in the time domain. And if we do this for each of our models, so speaker 1, 2, 3, 4, and our UBM, we can see them and look at them. We can already see that those are quite different. So the first speaker has overall a very lower power in each of those features, in each of those coefficients. And Yeah, okay, the UBM has even lower power in those features. So these are pretty much the output that the GMM trains on those features. And the output, the GMM now tries to find in the 13th dimensions of the input to find the Gaussian distributions and try to find everything in it. So yeah, it's pretty cool that it works with such little input data of 1 second to train a pretty okay version of a speaker verification, speaker identification, sorry. And yeah, if you want, you can insert your own voice, or you can play around with these variables. And I think that's pretty much it.